This video has been supported by Spinogy. Hey guys, I haven't published a lot of CNC content this year, have I? And so it wasn't a huge surprise when my Spindle manufacturer told me to return the barely used X32 kit. Sad but fair, I guess. Maybe I can 3D print a holder to mount this USB-powered Dremel tool to the Z-axis. Or I could return the shed to its original purpose and fill it with bicycles and lawnmowers and rusty replacement parts for them. Excuse me for a minute, there's some truck pulling up. Can't quite remember having any eBay accidents of this magnitude lately. And why does it say Spinogy on there? What a weird coincidence. OMG. It looks like this cubic meter of stuff is in fact a massive CNC spindle upgrade. Control cabinet and all. I have a feeling that my recent creation is about to be one-upped quite significantly. When I initially installed the X32 spindle last year, I was told that the control cabinet was only a rudimentary beta unit. There were still supply chain disruptions impacting VFD manufacturers and so forth. Little did I know what a huge deal was being prepared in the background then. This is it, the finished, much more capable product. The magnificent box in front of us is the result of a collaboration between the motor spindle experts at Spinogy and the motion control specialists at Brezel, Antriebs- und Elektrotechnik. They are a broadband service provider for motors, motor drivers, and pretty much ready-to-go industrial automation. One of their special competences is precise servo and servo drive technology, and this, I reckon, is why they were invoked. This is not a simple variable frequency drive, which we are used to in our CNC machines. It is a full-fledged servo controller that would be just as suitable for driving our X, Y, or Z axes, with encoder inputs and position, speed, or torque control modes. Oh, and a casual 6 kilowatt output power rating. What does that make our spindle? Oh yeah, there was one of those too. The huge output power makes it very large. Mr. Reps, any comments on that subject? And the built-in encoder makes it a servo motor, I suppose. X30 is a new product from Spinogy. It did not exist when I visited their factory. It's a larger, fully modular platform for motor power levels between 3 and 5 kilowatt. And just like before, the Spinogy online shop lets you configure every last little detail about it, while displaying immediate, fully transparent pricing for your custom spindle. I'm afraid I've never even come close to pushing my previous X22 to its limits. Yet for demo purposes, it seems like I've been given the fully pimped out package. The highest torque 5 kilowatt 4-pole motor windings. 30,000 RPM hybrid ceramic ball bearings made by GMN. Fluid cooling for quiet operation and the best dimensional accuracy. Multiple temperature sensors, and of course the highlight, a digital absolute encoder for closed-loop position control. Let's give it a spin, shall we? The HSK tool clamping system's claim to fame are the two contact surfaces, the cone and the shoulder, leading to higher stiffness, whereas most SK interpretations only rely on the cone. These jaws are the reason why we aren't supposed to run the spindle without a tool clamped. They are meant to grip a tool holder from within and only get tighter and stiffer at higher RPMs. The centrifugal forces, beneficial in that way, could also turn against us if there is nothing to grip. While upstairs in the lab, I'll just inject some compressed air into the appropriate port. Normally, these are, of course, operated under computer control with solenoid valves. Oh boy, this change also means an upgrade from HSK E25 to E40, which gives us a much wider range of tool diameters to play with. I believe these gorgeous power and sensor connectors are of the Intercontec SpeedTech series. Ordinary household outlets in Germany are normally fused at 16 ampere, so you can't get more than 3.6 kilowatt out of them. This new system with 3-phase power can all but smile at such puny limitations. Hey, don't look up. There's no electrical code violations up there whatsoever. Okay, now we get to navigate the many safety layers before we get our first movement. While still not a safety-first kinda guy, I appreciate them here. I feel like a giant servo with plenty of torque at every speed is potentially much more hazardous than the classic high-frequency spindle that starts out weak and is pretty much screaming while in danger mode. So here we have the usual red safety supervisor device that looks at a number of inputs and only actuates K1 when it is satisfied. By default, from the Spinogy factory, the safety circuit is mostly just bridged, with these red jumpers in the terminal blocks down here. The front emergency stop switch, I believe, is the only run condition at the moment. Downstairs, in the actual installation, we will replace the other bridges with the water chiller OK input, the compressed air sensor and the safety circuit from LinuxCNC. The servo drive has its own save torque off module which listens to the safety supervisor. When instructed so, it disconnects the whole servo drive's power output safely through reliable electrical means, even when the embedded software side is locked up. Oh, with a pretty long delay after pressing emergency stop, I might have to adjust that. Additionally, the servo drive has external digital inputs for enabling its power and logic stages. Here again just temporarily bridged for a quick test drive. Now we do still have an error 62 being blinked out at us, and that is interesting. Any guesses what this Ethernet cable might be for? Why don't we ask the manufacturer's configuration software about that? Ooh, nice. Don't think I've ever been so happy about an error before. This drive seems to be equipped with an EtherCAT communications module. You know, the superior technology that I just converted my whole CNC control system to. And it's just complaining about not being able to find a master. I don't have one here, so for our quick test to succeed, I have to disable it. It seems to have been deemed a safety critical error, and so it won't move with that. Yep, that's a few more green indicators. There we go, that's it. Well, that's a small part of it. I suppose in normal operation we will continue to use constant speed mode. But if all goes according to plan, LinuxCNC EtherCAT will be able to control this drive, like the other CIA 402 compliant EtherCAT participants. And then we can just use what's best for probing, milling or rigid tapping. Check out how little power it needs. I don't have reference values from before, but I'm pretty sure there is a substantial energy efficiency boost for closed-loop control over vector control or FOC, which our old Omron MX2 used. With synchronization turned off, the drive isn't trying to keep its position. Let's get a taste of some of that sweet, sweet low-speed torque. Oh yeah, there are some higher watt numbers showing up. Still, this is an asynchronous induction motor, thriving at high speeds, on the verge of starvation at standstill. So if we want to see some kilowatts, we need RPMs first. The fact that my pipe wrench has not yet been yanked out of my hand and thrown across the room indicates that some control loop tuning has already taken place. But it'll be interesting how this behaves in various scenarios. Like, surely not the same PID values apply to 30,000 RPM milling and 10 RPM rigid tapping. And for that matter, what happens with the encoder position at very high speeds? Like, I don't think it can keep track when we are really flooring it. And it doesn't have to. We only need precise multi-turn position at low speeds. But will it fail and recover gracefully at those transitions? Let's find out. The new control cabinet, to put it mildly, is huge. It needs some new mounting holes, and this time I'm not even sure if 2 will suffice. Hehe, just kidding. Or am I? This time we won't have to worry about common mode leakage currents across the communications bus, because the EtherCAT physical layer has coupling transformers just like Ethernet. The software side is going to be a bit of a chore though, unexpectedly so. After literally swooning over EtherCAT for years, this time I had to get to know it up close and personal. The affordable Chinese servos I've shown in the past worked right out of the box without trouble. Today's sophisticated made-in-Germany hardware forced me to take the plunge into this universe of acronyms. Let me show you what I mean. For its EtherCAT functionality, our new servo drive uses an outsourced Beckhoff ESC20 IP core on this FPGA, detailed documentation for which is only available to registered Beckhoff partners. So we've got to rely purely on what the manufacturer gives us. There's also an SII EEPROM on here, a slave interface identification something, which was delivered not exactly blank, but also not adjusted to the default config of the drive. My lead shine boxes seem to emulate this EEPROM to tell everybody who asks about all the currently configured exposed EtherCAT features and parameters, such as SM, sync managers or FMMUs, field bus memory management units. Meanwhile, our new tight-lipped Metronics box only tells us about its PDI, Process Data Interface, and some COE mailboxes can open over EtherCAT. Pretty sure this is a violation of some EtherCAT standard, but we do get a part of the missing information from the manufacturer's website. Not an EEPROM image, but an ESI XML file, an EtherCAT subdevice information document. What's outlined in this file complies with the CIA CAN in Automation 402 standard. Exactly the same thing that I already use to talk to my motion axes. So we should be able to just replicate that one more time, right?
No.
That's how it should work, but it does not. And I can't even complain about that. The open source EtherCAT master is not yet very widely used, and manufacturers don't test for compatibility there, much less guarantee it. They did, however, publish a TwinCAT 2 demo project, a paid industrial automation software in whose free 30-day trial we should be able to validate and export a working configuration. This is the normal thing that the usual customers will use, so that must work, right? Well, the PDOs, the process data objects, that are communicated every cycle for time-critical data such as target position, those don't seem to be prepared quite correctly in here. According to their own manual, they must not be longer than 8 byte, so these will have to be modified. I'll arrange something sensible here with all the controls I expect to need for velocity and position control modes. By enabling these two options, the TwinCAT software is able to use SDOs, service data objects, to configure our PDOs directly in the servo drive's volatile memory at every PS transition, pre-operational to safe operational state. But I have Metronics Servo Commander connected anyway for looking over its shoulder. Here we also have to adjust the cycle time, which was some odd value by default. This is basically the period for every one of which a new set of PDOs is expected. It should match the DC, distributed clock, cycle time, and the LinuxCNC servo thread. 1 millisecond would be a common value. Hope you're taking notes. This is all relevant vocabulary for the next exam. It wouldn't be too much to ask for it to work right now, would it? There is a shimmer of hope. The servo drive reacts to state transition requests, init, pre-OP, OP and such. And when in an operational state, it does seem to transmit real-time data, which is great. This is me manually turning the spindle shaft. But in the opposite direction, it doesn't look like the drive receives PDOs from the master. We should be going through the CIA 402 state machine right now, and ending with a control word 15. I don't know, I hate it, but I'm going to ask the manufacturer and the supplier for help. My head is still spinning after researching all the acronyms for multiple days now. There are still so many open questions, like what does a sync manager control byte do? Why did they define the EEPROM byte size as 128, but then gave it more than 128 bytes of content? I believe this causes malfunctions both in TwinCAT's EEPROM manipulation tool and in an open source equivalent called SII tool. I don't have answers to those questions yet, and the manufacturer did not deem my email worthy of replying to at all. But my message to Brezel Antriebs- und Elektrotechnik was heard, and they responded quickly with crucial information that I've not yet seen in any of the Metronics documentation. Apparently all active PDOs have to be filled up all the way to 8 byte. Half-Cs are not allowed. Even if the data is not needed, it needs to be padded. Good to know. Another seemingly important info was hidden very nicely, not in the EtherCAT and Can Open manual, not in the EtherCAT manual, but only in the error code troubleshooting section of the servo drive manual. From what I understand, the number of active PDOs must not be larger than this TP factor in the cycle time configuration. I'm aiming for 2 receive and 2 transmit PDOs, and I have to arrive at 1000 microsecond cycle times. Also useful to know. Lastly, the biggest mystery and one of the first things I suspected, the SII EEPROM. I used Synapticon's open source SII tool, link below, to create a mostly correct image file, and then I grafted the first few bytes of Metronix's original image onto it. Those for the PDI section and Sync0 enable most importantly. The result can then be flashed with the EtherCAT command line utility on Linux, and after one reset or power cycle of the servo drive, we finally got it. The thing is, the open source EtherCAT master relies partially on the SII EEPROM's contents, whereas Beckhoff TwinCAT prefers to have a local ESI XML file. That way the flawed default config may just work in most cases, just not in my scenario. I'll publish the EEPROM image in the GitHub repo, which is linked below. So that was a fun little excursion, wasn't it? A bit disheartening between the manufacturer's sketchy resources and all the club member exclusive low-level EtherCAT info, but not enough so to make me want to go back to bit-banked parallel ports and step direction impulses. Now time to take a few days off, erect a motor crane, disassemble the gantry, and drill some new mounting holes into the Z-axis plate. Unless... is this allowed? I don't see why not. I thought it would be wise to pre-drill the precise hole locations with a short, high-quality solid carbide twist drill. And yeah, it won't walk away, that's for sure. But following that up with a longer, larger diameter HSS twist drill does not sound exactly healthy. These get a stability benefit from tip engagement, which I have effectively taken away just now. But we now have such immense torque reserves that we could probably just stir weld our way through the plate, even with a completely dull bit. I've mapped some new PDOs to my old Spindle diagnostic readouts. A PT100 temperature sensor in the Spindle seems to be connected to and configured in the servo drive correctly, but it seems to have a plus-minus 30 degrees C reading tolerance? What the hell? Spinogy X30 still has its hang tab style mounting holes, for when only the front of a mounting surface is accessible. There are also 4 M8 threads for through plate mounting bolts. This time I'm going to use those. And then there are 2 more low tolerance bores for locating pins, which were included with the Spindle, but I can't use those. Their purpose is to eliminate any wiggle room, but I need that for tramming. And there we are, my old clapped out Honda Civic of a CNC machine with a brand new Ferrari engine. Over-spindled like crazy, but it can still lift it at least. Now I've made a few low RPM drill holes already, but before we are getting serious, we should run the grease distribution program, mandatory after delivery or a longer standstill. Reps could benefit from such a run too. Now that I've figured out how to make the Metronix servo drive behave, I can use D. Brown's normal LinuxCNC CIA402 component to take care of all the standardized handshakes with ease. The grease run goes all the way to 30,000 RPM in intervals, and it takes a while. Let's prepare some tools in the meantime. The Spindle kit included a couple of these gorgeous HSK to ER tool holders, as well as some Swiss-made RegoFix ER25 collet chucks. The UP, I'm told, stands for Ultra Precision, so we are on topic again. I'll try to measure some runouts in a moment, and maybe compare to the lowest cost collet chucks that eBay had to offer. Oh, the cheapos come pre-filled with some leftover metal chips from manufacturing, how generous. Overall, as a kind of broadband new spindle benchmark, I'd like to try and drill some 0.2mm holes, needing maximum RPM at minimal runout. And then I want to see some horsepower brutality at lower RPMs. I bought this anonymous second-hand face mill on eBay because it was cheap, and even if it would have arrived all worn out, I could have recycled the HSK interface for my Heimer 3D touch probe. Now, seeing it in person for the first time, I believe it has polycrystalline diamond cutters. Pretty fancy, not necessarily for multi-horsepower muscle flexing, but it should leave some great surface finishes if it's still good. For the adrenaline kick, I might have to resort to shredding some steel with this bad boy. And then something that I actually need to do, like productively, not just for spindle testing. I want to modify ferrite parts slightly, a very, very hard glass-like material. I've done that with some success in the past, with the previous Spinogy spindle, but I only had these super cheap Dremel diamond discs handy, inaccuracies of which caused chipped, cut edges. Now I paid €20 per piece for these, and I expect better results. Meanwhile, downstairs, the grease distribution run is completed and everybody should be warmed up. Also possibly important for best performance, the piston return pneumatic port is currently fed at least 3 bar. Under these conditions, the radial runout directly at the cone looks to be 2 micrometer. That's very good for a smooth surface finish, long tool lives, and a quiet operation. Let's see what a Spinogy branded tool holder does to that number. No change, still excellent. And now a Regofix Ultra Precision ER collet chuck. Oh, would you look at that? That does seem to have some runout in the 2 micrometer range, but we lucked out and ended up compensating for the 2 micron that were inherited from the spindle. What are the odds? And finally, the cheapest of the cheap no-name ER collet chuck. The whole 16 pieces kit set me back, €35 delivered. That is less than a single Regofix UP piece. Oh no. This is not prepared or anything. I literally just ordered and unpacked a random one. How do they even manufacture that? Like, you have to create a specifically eccentric fixture or something. Nope, no stray chips on the contact surfaces. But it seems to be lightly scratched now, so not a particularly hard material either. Yeah, well, no surprise. When ordering a precision spindle, it makes no sense to cheap out on the clamping accessories. Spinogy's supplied hardware is top-notch. Let's put it to use and make some chips. The tiny 0.2mm drill bit was a part of about 1 kilogram of solid carbide tooling from the PCB industry that I bought on eBay a long time ago. Used, probably nearly worn out and replaced prophylactically, but I hope it'll do a few more holes for me. I was thinking 35 with ever-increasing plunge feed rates, until it gives up and becomes a deadly supersonic projectile. The high-throughput industrial drilling machines that are working at massive PCB manufacturing operations are often running at 100,000 RPM though, so our mileage may vary. I'm just perforating some copper-clad FR4 substrate. Nothing special, but there are glass fibers in there, so not the easiest thing in the world either. There it goes. Better than I expected, honestly. Also a little less supersonic than I had expected. "20 holes means that we went up to 1140 mm per minute plunge feed rates. Good looking, reliable ones, maybe up to 1000. I'm afraid I've followed a wrong assumption in my ferrite slitting mission. While the high-quality diamond disc bit does have much better runout than any aftermarket Dremel stuff, I am beginning to suspect that that was not my problem. I have tried a 3D printed fixture before, but only to support the ring and keep it from being crushed in the vise after losing a section. Turns out they are strong enough to support themselves, but what I do need some kind of fixture for is to keep that cut-off piece in position. Otherwise, as soon as it hangs on its last little half-millimeter sliver, it inevitably breaks off and takes a big chip out of the material that I wanted to keep. Yeah, wonderful, just like this. What helped me succeed effortlessly and with the same cut parameters was to just glue the ring to some PCB substrate and to simply cut through both. The result are perfectly clean, parallel, chip-free faces. But this operation created a lot of nasty fine dust. Would not recommend if it can be avoided. Would also not recommend leaving in any precision machine interfaces. I don't know if that's news to anybody but me. But face mills are so much fun. In my long history of high-frequency spindles, I never had the low-speed torque to run one. Now I finally do, when starting at 2000 RPM or with a lower chip load. And it's just wonderful. The huge material removal rate is going to be a huge time saver in facing and squaring operations. The thick integral shaft of this random eBay tool makes it very stiff, leading to an impressive surface finish. But I think the teeth can't be replaced. This thing is meant to be reground when worn out. For my small-scale operation I don't like that, but we'll see if we ever get there at all. Can you see the airborne aluminium microchips? Those are really creeping me out nowadays. I've been CNC machining since my late teens, and who knows what horrors I've inhaled in all that time. I hope that lower RPMs and mostly computer-generated chip load optimized toolpaths will minimize those, but I'm also not operating the machine without a dust filter respirator anymore. Oh my, that is amazing. Rigid tapping. I was dreading it a little bit, to be honest, thinking that I would need to customize a CAM processor and the LinuxCNC CIA402 component to be able to switch back and forth between velocity and position control mode on the fly. But no, it's actually mostly fine and easy to get started. Only our lovely servo drive manufacturer had another spanner or two to throw into the works. But they won't stop me this time either. After selecting rigid tapping here, Fusion 360's default LinuxCNC CAM processor will put out the correct G-code, G33.1, specifying the final depth Z-coordinate and a K value, which is simply the distance per spindle revolution or thread pitch. For this to work out, a LinuxCNC spindle needs 3 or 4 signals that are otherwise optional. A spindle at speed bit which says when the RPM set point has been reached, and a velocity, a position, and an index impulse signal, which would normally be provided by a rotary encoder. Our spindle encoder is only connected to the servo drive, and there is no easy way of grabbing the data directly from it. We can, however, get real-time position and speed feedback over EtherCAT, which are 2 of the 4 required data points. The first thrown spanner is related to the spindle at speed signal. According to Metronic's documentation, the status word bit 10 should indicate target reached both in position and speed control modes. There is even a specific window comparator prepared just for this bit in speed control mode, but in reality it only works in position control mode. As a workaround, I've constructed a little hell mechanism that compares RPM set point and feedback. and judges if they are close enough together for long enough, giving us the third required signal, spindle at speed, at which a tapping operation can start. The final puzzle piece, the encoder index impulse, is also a start condition. By waiting for this impulse that the rotary encoder normally puts out exactly once per revolution, a tapping program can ensure that all threads start in exactly the same orientation. And if we break a tool and have to rerun the program, we can avoid cross-threading. I haven't found any PDOs that are outputting anything like this directly, but there is a shaft angle object which is representing as a number between 0 and 1000. In hell, I could convert that number to a single bit. It would come out to 1, always, except once per revolution at a 0 angle. A suitable index impulse right there. In the end, I'm using a custom real-time component written in C, because the hell workarounds were getting long and hard to read. And there is another quirk where the tapping system wants to reset the encoder position to 0 above every hole, rather than memorizing those positions and returning to those. It's inconsequential and dealt with. The custom component for this can be found in the LinuxCNC forum, and I've mirrored it in my GitHub repo, which is linked below. It works. Rigid tapping, everybody. Had we been normal pedestrian encoder users, no workarounds whatsoever would have been necessary. The other Metronics-specific problem is the rumbling that you might be able to hear in the background. The speed controller is a bit noisy, especially at low frequencies. That doesn't matter normally, but now we have a 70 kg Z-axis, trying to imitate that noisy signal in real time. The motion axis is slaved to the RPM feedback, so that if something stopped the tap, it wouldn't get crushed or yanked out of the material. I'd like to try the auto-tuning in Metronics Servo Commander software to get rid of the noise, but it gets stuck in its first step. Apparently this function is just not available for asynchronous motors, so I get to do some fine-tuning manually. Tappy tap tap. Although M10 in an 8mm plate is maybe a bit too much to ask if I'm being honest. And a hardware store quality tool is also not doing us any favors here. Nope, we noped out on first contact pretty much. Maybe with Anlauf. Oh, I've seen some chips at least, but still no. According to Spinogy's manual, our pimped out 5 kW 4-pole motor, with the encoder option, should max out at about 2.7 Nm, all the way from standstill to 15,000 RPM, at which point just inertia should give him even more oomph. If this tool is to be believed, that should be plenty for all I ever expect to need, but maybe this is only for this manufacturer's products. I briefly tested the holding torque at standstill with a fancy calibrated Mark 10 torque meter. No, don't you even think about it. It looks like in position control mode I'm not getting a holding torque much higher than 2 Nm, and that tracks with the warnings I've seen while adjusting the servo drive's cycle times. Doing so changes everything down to the power stage PWM frequency. And so any prior fine-tuning has probably been invalidated for most of this video. Let's try to change that in Metronics Servo Commander. We are given a built-in so-called reversing generator that can dictate a position target in the shape of a square wave basically, and an oscilloscope with which we can watch the effects of that. By tweaking the speed controller's gain, time constant and filter parameters, we can achieve nearly perfect tracking, but always with some vibration modes on top. Since neither milling, drilling nor rigid tapping rely on a position control mode, I chose to sacrifice this delicious snappy step response for a low noise, steady speed signal by ramping up the time constant and speed filter a little bit. Afterwards, in coordination with Spinogy, I increased the motor current limits slightly, which brought me to 2.5 Nm, and that is honestly close enough to the 2.7 spec. I feel like we could go even further than 12 ampere peak, because the motor windings are only 1 ohm or so. But I guess as soon as we leave the comforts of standstill, we have to look at complex impedances, with magnetic field angles and slip and all that dominating our total power loss. So there is more to it than a simple Ohm's law scenario. And I don't even think I need more talk than this, so let's not overdo it. Okay, I'll put it back where I found it. Realistically, the largest thread I could see myself automating would be M6 in the foreseeable future, because that is the standard thread for optical breadboards. I can always use thread milling for everything beyond that. This is a well-oiled M5 right here, and it goes through like butter one way. But then gets stuck on the return curiously. I guess this is not a spiral flute machine tap, so it's now packed with chips. No doubt this would have worked beautifully with the correct bit. This is what I would consider an adequate spiral flute machine tap. It encourages its chips to leave the working area through the top, so the flutes don't get packed and periodic reversals for chip breaking are not necessary. This is still easy, so I'll accelerate it by 100 RPM after every hole to keep things interesting. Starting at 200 RPM, which I would consider reasonable. That does not sound super good anymore. And the servostats confirm there is a higher load now on exit than there was on entry. I could imagine either because of aluminium sticking to the tool, or a small encoder position deviation for some reason. Uh-oh, it's getting hectic, and we are developing enough heat now to evaporate WD-40. Oh, the aluminium is being bent because something in the synchronization can't keep up apparently. Every last one came out as a functional M6 thread. Just after 600 or 700 RPM do they start to feel loose. How about M8 mate? An 8mm diameter machine thread, or roughly 0.pi inches. Did I ever mention how much I love big chips? These guys will be so much easier to clean up than the disgusting micro stuff that sticks to everything. Looking reasonable, but I only went a few turns deep for testing. Still looking reasonable at nearly full depth. Please ignore the mangled remains of the previous tap. I left it there as motivation for this guy. Let's go all the way through and also faster until something fails. Please don't tell the United States about the oil reserves in my CNC machine. Hey, I think I see a problem or an opportunity for improvement. Watch the workpiece exactly at the turnaround point. There seems to be a small, short-lived deformation, as if the spindle is exerting some axial force, and then we nearly get stuck on the way out. Those two have to be related, right? On the bright side, while nearly getting stuck, the Z-axis slows down perfectly in sync with the spindle, so that part is working wonderfully. I wonder if the system's spindle acceleration is too good. It slows down, comes to a stop, and reverses back out in the blink of an eye, in only a handful of LinuxCNC servo thread cycles. Here's what safety-first fanatics and their mandatory interlock doors are trying to take away from us. Give your hard-working CNC spindle a helping hand every once in a while. This is a success, but let's see if we can also defeat M10 this time, by limiting the acceleration and imitating older or larger machines. Sadly no, not with an all-in-one tap like this. In fact, this is significantly harder than M8, so I can say with confidence that that's not happening. Thread milling would work, of course, effortlessly to much larger sizes. But I am pleased to say that I found the acceleration and deceleration settings in the Midtronics servo settings, and those made the turnaround point so buttery smooth. Absolutely no hint of that residual jerk movement anymore. Beautiful. Here's a bit of speculation of what may have been happening. Without any limits on acceleration, the speed controller would approach new set points, enthusiastically and overshoot slightly. This bouncing's frequency could coincide with the EtherCAT sample reading rate, which in turn would trick LinuxCNC into seeing only a part of the values, and that would cause it to follow with an incorrect Z-axis position from here on out, producing loose threads, getting us stuck on the way out and so forth. Just a guess, but it sounded clever in my head. This is with a pretty conservative acceleration limit, I think 5000 RPM per second. There is so much technology between these two spinny things. It doesn't look like much on the surface, but seeing them coordinated with low latency is impressive. I would say this is kind of already a viable business model. Like there's gotta be a huge market for just thread grid plates. Welding tables, optical breadboards, and mounting plates for the DIY CNC niche. Easy money. It does need permanent lubrication though. As the grand finale, let's try and pulverize some carbon steel with a 16mm solid carbide end mill. This is a €90 tool rated for full slot milling, with up to 1 diameter depth, as well as straight down vertical plunging. Unlikely on this machine to be honest, but I'd be very happy to see it do something, anything impressive. In before, multi-million-dollar muscle-bound, Titans-style showroom chips, with dubstep. The victim in this case I believe is a steel alloy called 42CRMO4. It took a few attempts to find cut parameters that aren't entirely hopeless. This is literally my first time using such a large tool on this machine, and a brand new unfamiliar spindle too. It doesn't sound happy and we are not going fast, but we are chipping away at a very resilient material, at only slightly over 3000 RPM but pushing out a lot of power. As long as that power is going into the chips, it's okay, I guess. But this looks like it wants even lower RPMs, or else it's going to wear out my fancy tool in no time. But it's clearly possible to use such a monster. However, our spindle reaches peak performance not below 15,000 RPM. As a consequence, its comfort zone is kind of still in the smaller diameters and fewer teeth. With such an end mill, we can really go to town. Except I'm still missing flood coolant. Time to start building a new machine. Wow, this sure is a mean material. And here's the aforepromised easy thread milling in that material. M10, with the added advantage of being able to choose the precise diameter down to the micrometer. And that is all I could think of trying. Thank you so much for watching. See you soon with some real practical jobs for Spinogy X30.